Can you hear me all right? Okay. Thank you so much for the invitation. It's really great to be here talking with you and hearing what's going on this side of the Pacific Ocean. I'll start off by saying that I am deeply respectful of the multilingual approach and 100% agree that everything shouldn't be English, but everything I'm going to show you in this talk is about English. For reasons that I'm happy to talk about offline. I think it's hard to do well at everything, and we're a small team. So we made the choice early on, against my protest, for our models at Allen AI to be English focused. We even filter for English, and I'm deeply embarrassed about that when I come here. But it was so that we could do other things well. And I hope that in the future, we'll be able to work together more closely internationally. So this talk is titled Science of AI and AI for Science, because I had to give a title before we were finished training our latest model. And so where we are now, my thesis in this talk is that it takes a dynamic flow of continual development to advance language model research and applications, and also to build the models themselves. And this idea of a flow is going to be a recurring theme through this talk. So if I was asked this morning what I should title the talk, I would title it Model Flows, Powering Science of AI and AI for Science. So hopefully by the end of the talk, that will make sense to you. A model flow is our way of talking about the fully open release of everything that you need for reproducibility. So for all the many increasing number of training stages that we talk about when we build language models, we need all the data. We need the weights, of course, at the end, but also the intermediate checkpoints along the way so that people can reproduce and understand what's happening through those training dynamics and evaluate more richly than we were able to do. Detailed recipes for all the protocols and the code that you need to rerun the training, and of course, extensive documentation and analysis. So our release of Olmo 3, which was just Thursday, this is actually the first time I think anyone is giving a talk about Olmo 3 since its release. It's the whole model flow, and you can see we actually have three final models that we've highlighted, and so each one corresponds to a different post-training path after building the base model over there on the left. So we'll talk more about this, mostly from a data perspective, in the second half of the talk. I'm going to start off by kind of motivating the whole, why it's important to have the whole model flow and what it's good for. And this isn't the whole story. We had some great conversations at lunch about some other reasons you want a model flow. I'm going to focus on enabling research. I'm part of my time, I'm a professor. I have graduate students, some of whom don't work on the Olmo project, and I like to enable their work with what we do and the work of PhD students who are here and all around the world. So that'll be part of the talk, and then I'll talk very briefly about some science accelerating AI applications, and then I'll turn to Olmo 3 with, again, mostly a data perspective. So again, when we release the model flow, we are releasing training data. And I'm going to argue that having open training data enables all kinds of new ways to think about traceability, data auditing, data accreditation. And so the first project I want to talk about is OlmoTrace. This is a really interesting and unique feature that we offer with our demos of the Olmo models. Essentially, after a model generates a response to your question, this is a question about pop artist Celine Dion, if you enable OlmoTrace, some of the text in the answer will be highlighted. And what's happening here is exact match search for long spans of text in the model output that match back to the training data. And then you can, because we released the entire training data set and we've indexed it for this rapid search, you can actually follow those highlighted passages back and see them in their original contexts. Now notice, we're not saying this is why the model gave this answer. We don't know why the model gave the answer. It's a neural network, it's complicated. But we can say that this text was observed by the model during its training, and we can see the context it was observed in. So OlmoTrace there's some algorithmic magic behind it. It's searching a multi-trillion token data set in real time using a tool called Infinigram, which we published in earlier work. It's using essentially suffix arrays, if you're familiar with your data structures. People are using it for fact-checking, tracing creativity, debugging, and data traceability for governance. How do we do it? This is huge. The amount of data that we need to index if we're going to trace through trillions of tokens, is possibly as large as a petabyte. In fact, we indexed a petabyte of data. This is maybe 24 to 400 times the amount of text in the US Library of Congress. I asked 2 different language models to estimate this ratio, and it's actually unclear. To do this, we've continued to improve the underlying data structure. We learned from colleagues in bioinformatics about a data structure called FMindex. And in work published at EMNLP, actually led by a UW undergrad and receiving the Best Paper Award, we introduced Infinigram Mini, which gave an 18 times speed up, benefits to memory use, and works in real time with extremely large corpora. Again, this is doing exact sequence match. Something that has been done in bioinformatics for a long time, but hasn't been quite so widespread in NLP. So diverse AI research includes better data access. We like to talk on the right. I've got this figure showing the relationship between data, models, and evaluation. This is another kind of flow. The development of these models requires repeated feedback among the different teams and researchers who are working, and engineers who are working on these different parts. And so that part, I'm talking mostly about the data, but there's also maybe some important concerns around modeling, because it turns out not all the data can be open. There are some obstacles. When we build language models today, we generally assume that hard decisions are made about data being included or not included, and that the people building the model are going to have access all at once to all the data that's required to do the building. But in fact, there are lots of constraints. Sometimes there are geographic constraints on where data is stored, or data can't be shared, as in healthcare situations, or data comes available at different times. There's expiration dates, or you need to update your model after it's been built due to new conditions in the world, new news. Owners of data might require the right to opt out of having their data used by some model users. There may be all kinds of regulatory concerns. So in light of this, I want to talk a little bit about modeling approaches and opening up the space of modeling possibilities that will allow us to maybe more continuously grow language models instead of doing one big run once a year like we typically do at AI2. We'd like to be able to add data, remove data at any time, and maybe even distribute the training so that data owners can locally train their models without sharing everything centrally. So we're not the first to think about this. There's been a lot of work on, for example, merging models. So here we have kind of a setup where you start with a public data model on the left, and then everyone builds a branch of that model, updating its parameters on their own data. And then you can merge these back in what's now known as a model soup, or some kind of ensembling. This just doesn't work as well as building a model in a more centralized way. And so despite some exciting early work, some of this was done by my students, this didn't really catch on. Another option that's been around for a long time in machine learning is federated learning, where it's sort of similar, except you have periodic remerging back. The problem here is that everybody has to be working in sync, and nobody can opt out, because eventually all the parameters will depend on all the data due to that remerging. So what we introduced is a solution called FlexOlmo, which is a more modular approach to distributed training that's going to allow everyone to contribute their data without sharing their data. And it will allow easy data addition and removal based on these different data ownerships at inference time. So I'll give you a high-level idea about how it works. The idea is you start with a mixture of experts, and you start by training an MOE on public data. That's there on the left in blue. And then let's take one data owner, say, I don't know, a newspaper in New York that wants to contribute data. They're going to add some new experts to that model and locally train it, updating only the weights for those experts, those feed-forward network parameters that are connected to the experts they are adding to the model. The originals are kept unchanged. And we may have, other organizations doing the same thing in parallel. The key to making this work at the end of the day, when we merge all of these different modeling components, is that each contributor has to train a domain-informed router that learns to separate tokens between the original public data model experts and the new experts. And if they each do that pairwise, we can then combine those routers at the end and get an always router among all the experts. This is explained in more detail in the paper. At the end, if that newspaper in New York wants to opt out or disallow some users from using their experts, this is quite straightforward. Those experts and the router component that ties to them can be removed at the end of the day at inference time, giving greater control. We show in the paper that this does not come at a big sacrifice in performance. The FlexOlmo model retains about 90% of the benefits of just doing a big MOE that sees all the data all at once, and it does better than the specialized experts would do if there was no merging. We're also applying this in a really exciting setting. So the data privacy concerns here were inspired by healthcare. AI2 has become a partner, a founding member of the Cancer AI Alliance, which is 4 leading cancer institutes in the United States collaborating to share data without really sharing data because they cannot share their data due to privacy. But we're working together with them to apply techniques like FlexOlmo to allow study of cancer data without sharing the data. Okay, so better data control is another thing that comes from having the model flow. We couldn't have built FlexOlmo without fully open data sets and models for experimentation. There's a third piece, and this focuses more on evaluation. And thanks to Yusuke for the excellent talk about evaluation and Satoshi for talking about the safety side of this. Speaking generally about evaluation, I think we're in a crisis where the creative uses people are coming up with for language model-based AI are well ahead of what we can rigorously evaluate. And we're all dealing with this in interesting ways. It's presenting a lot of opportunities for researchers. And so we're seeing an explosion of benchmarks, which is great. But when you're building language models, you have to make decisions about all kinds of things, and you want those to be driven by data coming from benchmarks. So for example, a pattern we see very often in our work that I'll come back to again and again in this talk is how to mix the data. What is the right ratio of sources of data when you're doing any particular stage of training? So in order to make decisions about data mixes, we need evaluations. We need benchmarks that are both aligned to the target capabilities, but also that give us really nice statistical properties so that we can cheaply make good decisions. So I think the common tools for this are train a pair of small models, see how they do on the benchmark you care about, and pick the one that does better, or maybe do a kind of scaling law where you train small models at different sizes, measure the performance, and extrapolate farther out. And these are beautiful ideas, but a challenge with both of them is that evaluations don't always look like nice smooth curves like we saw in the last slide. They're often quite bouncy, and it's often quite a while before you can see real differences, visible differences between them. And so there's a phase where you're spending a lot of compute evaluating small models or models on the scaling curve that's just not going to give you much information. So what we want to do is come up with actionable quantification about which benchmarks are useful. And our tool for that is building on a classic idea from signal processing called signal and noise. So on the left, we have an example of a data set, HeliSwag, which has, this is actually, so it has relatively low noise, in that the curves are pretty smooth, but it doesn't have great signal because, as you can see, a lot of the models are all bunched together there at the top. So this is not a great discriminator among different approaches to, for example, data mixing. In the middle, we have ArcChallenge, which has really good signal. The models are all separated out from each other pretty well, but each curve is really noisy. And on the right, we have everyone's favorite benchmark for some time last year, MMLU, which has both high signal and low noise. So in this paper, which is appearing at NeurIPS, I guess in a couple of weeks, we give a simple way to quantify both the signal through relative dispersion and the noise through the standard deviation of the last few checkpoints, which we find correlates with other kinds of noise. And the beautiful thing about this is that while neither signal nor noise alone can explain rank agreement from small to large scale. So think about scaling laws. You want the predictions at small scale among the quality of data mixes to hold up at larger scale, which you can't afford to run. Neither of these does a great job of explaining it, but SNR, signal to noise ratio, does. And that's the last plot on the right, where we have a R squared of 0.6. So our interventions in the Olmo 3 project involved, in many cases, selecting benchmarks and metrics that had higher SNR so we would get more out of those evaluation runs. Okay, so that's a whirlwind tour of a few research projects that we've done this year that build on what we have when we have the full model flow, focusing on data, on model, and evaluations. There's many more I could talk about, but I wanted to give a taste of why we do this. The other part of the story is, of course, building real applications. And so I'm just going to very briefly advertise two projects that came out this year. One from led by Akari Asai, who's now at Carnegie Mellon and still at Allen AI part-time, called Open Scholar, which uses retrieval augmentation to build tools for scientific literature. And it includes credible sourcing with attribution, and because of RAG, you can be up to date with the latest literature. Our most recent release in this line, which was just last week, is Deep Research Tulu, or Dr. Tulu, which provides long-form multi-paragraph answers that incorporate external evidence and also fine-grained attribution. And this is a reasoning model. And the technical innovation in this work, which I think is really cool and I won't have time to talk about, is reinforcement learning with evolving rubrics. Really, really elegant idea. You can see more in the paper. We have a lot more plans for building scientist-oriented applications. So in August, it was announced that the AI2 is leading a new project funded in part by the National Science Foundation and in part by NVIDIA to build open multimodal AI infrastructure. That's National Science Foundation language for more Olmos, specifically focused on the scientific research community, broadly construed. So what we want is more tools like Open Scholar and Dr. Tulu that are drawing input specifically from scientific communities, helping scientists to integrate their own data in its own modalities with their literature to accelerate scientific work. So this project really just got kicked off and has several university partners. Really excited to be leading this work with the support of the NSF and NVIDIA. Okay, so enough why. The rest of the talk, I want to talk about what we did and how in the Olmo 3 project. So I think the reason I was invited to speak here is the success of our Olmo series, which has been consistently the best fully open model, at least according to mostly English benchmarks. And we've been doing this, I guess, since 2020. We launched the effort in early 2023, late 2022, started releasing shortly after with our first 7B model, and we've grown in size. Not shown here are some variants like the mixture of experts that came out last year. Our general philosophy and guiding principle here, out of necessity, is to do the best we can at the lowest cost. And so we often publish these sort of Pareto curves showing approximate flops to train a model where they can be estimated and the performance on the y-axis. And so the Olmo 2 models were a really exciting contribution in that space, often performing at the same level as much more expensive models, and of course also setting a standard for openness by releasing the whole model flow. Olmo 3 was just released last Thursday. It was a huge team effort. It's a huge team by our standards. Most of us are coming out of a more academic atmosphere. And I think we've heard this already through the day. We have to get a lot of people to work together. This is still orders of magnitude less people than I think the big labs have. So I'm extremely proud of what the team's been able to accomplish. That QR code there is for the whole tech report, which gives you way more detail about all the things you're going to be annoyed with me at the end of the talk that I didn't cover. The main result here is that we release the whole flow, so you can see checkpoints along highlighted here where we evaluated along the entire series of stages. We're now up to 6 different stages. We've got the best fully open 32B model. I think the best, maybe the only only fully open 32B thinking model, which is performing about as well as Qwen 3 32B. On our final adapted evaluations. I'm not going to focus a lot on which evaluations are in our suite. I will say that we take pains to hold out evaluations that we don't use during development for the final tests. We do a lot of work to decontaminate the data so that we get honest numbers. In general, what's not shown in this graph is our, again, quality divided by cost principle. So we like to brag that Olmo3 has a data budget of about 1/6 of Qwen 3, and we're performing about as well. And we used about 40% of the compute per token compared to Llama 3. Okay, so again, there's a lot that I could talk about in terms of what it takes to build a model flow. There's algorithms, infrastructure, how you organize the team, experimental methodology. We've heard about some of this from the other speakers. It's all detailed in the Olmo3 technical report. In this talk, I had to pick a slice to go through that would be, manageable in the time we have. So I'm going to focus on the data. So the data that we choose is going to depend on the capabilities that we want. And our priorities when we sat down to plan Olmo3 were thinking and reasoning, which is becoming very, very exciting and important because it seems to open up new capabilities well beyond what's in the data. Tool use and agents becoming very important for the obvious reasons. And again, this partnership with the National Science Foundation, scientific applications have always been kind of in our wheelhouse and a major focus at AI2. So if you want to do those things, coding is going to be very important. Complex math seems to be a driver for thinking and reasoning. STEM papers seem central to scientific applications, and all of these are well served by having longer context. So that leads to having these different stages. You'll see we have the standard pre-training and mid-training, followed by a long context extension phase leading to our base model. And then there are three different pathways here with different foci. I'm going to focus in this talk just on the thinking model, assuming we have time for talking about the post-training phase, which I think we will. So our pre-training data set, again, fully open, is we call it DOLMA 3. It draws from, shouldn't be any surprises here, I think, except maybe the second one, which we'll get to in a minute. What I want you to notice is that we build a 9 trillion token pool. And then when we mix, you'll notice that the number of tokens drawn from each of these sources can go up or down. In some cases, we're downsampling. In some cases, we're upsampling. So we'll talk a little bit about how we build the mix. I want to start by talking about this possibly slightly interesting and surprising contribution on its own, OlmoCR science PDFs. There's a huge amount of data on the web that's not easy to use because it's in it's documents, right? It's essentially images like PDFs, which is not ready for feeding into a language model. And so we decided to develop our own efficient model to convert any document into training data for language modeling. We call it OlmoCR. It is, of course, language model based. We used it to build a trillion token data set from PDFs that we couldn't have unlocked if we didn't have a low-cost optical character recognition solution. So you can try out OlmoCR on the web demo. It's also one of the cheapest options for high-quality OCR. You can get the same quality on our benchmark as GPT-4o, possibly higher, at 1/30th of the cost. We have two technical reports about OlmoCR. The second version was released pretty recently. This is an example of the kind of thing it can do. That's a really gnarly photograph of a page. It's got all kinds of artifacts on it, bad lighting. But OlmoCR does a great job, and it's document aware. It handles footnotes. It doesn't put the weird symbols in that you often get with OCR. Really, really exciting and high quality. And we also released all of this fully openly. So we have one of the highest quality OCR systems we were able to benchmark, but it's also fully open. So you can download it, use it, improve it, and so on. So on both these two largest contributors, the web data sourced from Common Crawl and the science PDFs, we did extensive extraction, filtering, deduplication, and quality classification. So I'm going to talk a little bit about that process. This is the sort of flow diagram for all the stuff that happens. You see the OCR text extraction is really just the first step for those academic PDFs. There's more filtering, deduplication, fine-grained classification. This is a little bit more detail on the web data. We start with 255 billion documents. We do filtering for PII, for language. Again, we're focusing on English. We remove URLs. And then there's extensive deduplication of several kinds. There's exact deduplication with new tools made available, fuzzy deduplication. There's a suffix array to help us remove boilerplate from this data. And after we've done all of that, we get down to about 10 billion documents, and we use this really nice tool called from a paper called Organize the Web. We call it Web Organizer, and it basically breaks things down into these more micro domains of different kinds. So I like to think of this as the next generation of quality filtering. Quality is domain topic specific. So you can do a much better job of curating good data if you categorize it and then do the filtering and mixing after you've done that fine-grained work. We do extensive empirical testing to explore how to properly blend these many different fine-grained sources. At a high level, the way we do this is we do swarm runs, small models, lots of small models trained with randomly sampled mixtures. So P is just the mixture weights across all of those domains. We fit a regression model on that to try and predict downstream performance, and then we solve an optimization problem to find the best P star. And this is repeated, and there's a lot more to say about it. A new paper coming out relatively soon on what we call Olmix will describe these procedures in a lot more detail. And really, the people who led this effort point out to me that diagram we have in the paper is hiding really a whole lot of expert labor and a whole lot of feedback loops where you go to the next stage and then you go back and realize that you need to improve your deduplication or your filter wasn't quite ready yet. Huge amount of loops through this process. You could almost call it a flow. The other thing I want to mention briefly is these other sources, which are a smaller proportion of the data set, but they're really high value sources, and they've actually been upsampled. So various findings have shown that repeating the same data in pre-training isn't necessarily a bad idea, especially if it's good data. So you'll see some of these have been repeated multiple times in the final mix. And the way we did this is based on quality scores. Where if a document gets higher quality, then it's going to have a higher probability of getting sampled more times. So much more detail about that in the tech report. Okay, so pre-training, there's this tension between scale, having lots of data, and high quality data. And so I think of the pre-training phase as really scale. Obviously, we want high quality data there, but this is going to be 99% of our budget, trillions of tokens, and then after we've used most of our compute budget, we switch to this mid-training phase, sometimes called annealing, where you use the last 1% and really upsample high quality in-domain data, sometimes even using the same kinds of data we use in supervised fine-tuning. And this is like data that's really, really good, but if we used it in pre-training, it would probably get washed out because it's really small. So what's in our mid-training mix? We call it DOLMA 3 Dolmino. More focus on math problem solving through code and discussion, instruction data sets. Again, those high quality STEM PDFs that were extracted with OCR. Lots of synthetic data that was rewritten to get diverse question structures, huge amount of text rewriting here, and math and code problem solving using human-inspired meta-reasoning strategies and traces. This effort was really quite fascinating from a team organization perspective. We had essentially a whole lot of different people on the team working in parallel on different capabilities and different data sources, and they would do this iterative process and continue to improve the data synthesis or the data curation and kind of work asynchronously, but then occasionally we'd bring everything in for centralized integration tests and feed that information back. We'd do occasional SFT tests to see how things transferred when we kept going to the next round. And what's going on when these people are iterating? I don't know. This is a slide from one of our data leads, Kyle Lowe. I think this illustrates really nicely what it feels like to build a language model. In the first phases, you look at your data, you look at your output, you look at how your model is performing, and you see lots of obvious problems. You see stuff that's not language, you see spam, you see stuff humans can't read, you see adult content and toxic, and so you iteratively are improving the filters and the different tools that are processing the data and curating the data, and eventually you hit a point where you're not seeing obvious problems as often, but you know they're probably still there. And so the general principle we've discovered is that there's diminishing returns for human intuition to keep contributing here, and it's time to switch to experiments and put your effort in towards iterating on checking for usefulness and ways that you could improve the data. There's a lot more trying to illustrate this in the paper. I want to briefly mention decontamination. So we have some statistics on how much contamination we found from different benchmarks in different sources of data. I believe this is mid-training data. Yeah, these are mid-training data sources, and you can see a lot of variation. You can see some data sets are really heavily contaminated. What's also interesting, and I should have called out the numbers, is that there are data sets, there are benchmarks where there's high contamination, and it really does explain why the performance is good, because if you take it out, you see a big drop in performance on that benchmark. But there are other cases where there's high contamination, and if you decontaminate, it doesn't seem to make a difference. So this is an area where more study is needed. I tend to lean conservative and think that it's better to decontaminate, because that was always what I was taught as a student in natural language processing back in the early 2000s. But I think the results vary quite a bit on this, and so you can only do this if we publish the model the data alongside the model. I mentioned the signal-to-noise tool earlier. This is an example of it being used, one example among many, but we're trying to pick a good average of evaluations to use for coding. And you can see one mix over there on the left, and it's just a total mess. And the signal-to-noise ratio is about 3.2. As we aggregate more, reduce noisy tasks, we improve the SNR to 6, and then once again, once we've tuned the final configuration, we get to a signal-to-noise ratio of 10 and much clearer plots with much nicer information. So this is an example of how evaluation and data and model runs are going hand in hand. I'll briefly mention long context extension. We pre-train this set of models at 4K, and we extend it in this phase up to 64K. If you look in the literature, there's a huge amount of variation in how much data people use for long context, less than 20 billion in some cases, sometimes more than 800 billion tokens. What kinds of data to use? Some people are using synthetic data, classifiers to automatically detect long dependencies. Others are using books or code. People do it at different phases, before mid-training, after fine-tuning. We developed a recipe. We've got a 600 billion token corpus we call the Longmino pool. There's lots of interesting things in here. We use gzip to determine which of this data is least and most compressible and chop off those outer parts of the distribution. We do data augmentation to add some stuff at the end to force the model to learn how to look back earlier on. There's also some short context stuff added in, so we don't lose ability there. And there's some best fit packing that goes in. There's also interesting interactions between the rope extensions with Yarn that you apply to the model and the architecture. So it turns out that it's better in our case to apply Yarn to full attention layers, but not the sliding window layers. Lots more in the paper and a forthcoming report by Amanda Birch. I think, yeah, we can keep going. So I'll talk a little bit about what happens on the thinking pathway through our post-training. I'll just mention briefly, we also release an RL0 model at the 7B scale, which just does RL directly on the base model, and an instruct model at the 7B scale, which is focused on more things like tool use and so on. That instruct model, we're working on getting a larger model out, but the 32B wasn't released. For the thinking model, there's a 32B and a 7B. So our work in post-training builds heavily on our past efforts on open and reproducible post-training. Way back, we released Self-Instruct, which started the trend of using synthetic data to improve instruction following. And we've continued to curate and collect and evaluate open instruction tuning data sets and algorithms for preference tuning. We introduced reinforcement learning with verifiable rewards around the same time that DeepSeek came out. And got us to our Tulu 370B model, which was on par with some really strong models elsewhere. Our data set for fine tuning for thinking is called Dolce Think. There's a lot of prompts that are drawn from open data sets, as we've done before, but we add synthetic reasoning chains to help the model learn from other models that generate reasoning chains how to think. There's also extensive filtering here for license, for incomplete reasoning chains, for topic, for mentions of other models. We want our model to talk about itself and not other models. There's more language ID. And again, data mixing, decontamination, the same kinds of things we saw earlier on. The next phase is, of course, preference tuning. And the interesting novel element here is that we use a technique published by UW student Scott Gang very recently called Delta Learning, which uses quality contrast between completions. So essentially what we're doing here is you take a stronger model and a weaker model and look at the contrast between the quality of those rather than just pairwise preferences. You get a delta. And this makes a big difference, discussed much more in the paper. Finally, we of course use our RLVR technique. A couple interesting things here. We do something here called difficulty filtering. So we don't want to train on stuff that's too easy. So we do rollouts for each prompt. And if we find that the model's already getting the right answer, which is automatically verifiable with these kinds of tasks, like in IF eval, you remove that example if you get it right 5 or more times. We also noticed something really interesting in the data mixing phase, which is that one of the dangers with RL is, of course, overfitting. We found that if you only include data for IF eval, you do well on IF eval, but you start failing on something else like alpaca eval. That's the drop in the pink curve on the right. But if you use a mixture, the different capabilities you're driving for tend to help each other out in avoiding overfitting. I guess I have a little more time, so I could have gone into more detail on a lot of these things, but I would have felt rushed. There's a whole lot more in the paper about with all the performance numbers, which I didn't really put in the talk across the whole flow. Deeper discussion of our methodology and evaluations, benefits of things like souping, energy use assessment, our OMO-RL recipe for expanding verifiable reasoning beyond math and code. Lots of good stuff there about making RL runs more stable and improving efficiency. The Dolce Instruct data for post-training the Instruct model. And a whole ton of experiments that will, I think, open the door for improvements in design and recipes and so on and so forth. So please take a look. We did this so that the research community could build on it. I would be absolutely thrilled if some of the tools we built in Olmo 3 help in teams building models that include other languages as well. So success in building the model flow came down to how we could better look at, understand, use, and mix the data. I think the data is often overlooked. Where are we headed next? At AI2, we are committed to continuing to build AI that works better for people. So continuing to look at reasoning and tool use, complex tasks that are making data collection more challenging. And hopefully we've shown some way forward there and given some more tools and techniques that will ease that burden for others. We are also very excited about new paradigms for data. So like in FlexOlmo, more modular access to data and more credit for data owners. We are also, I didn't have any time to talk about any of our multimodal efforts today, but our work there, I think multimodality and working with different forms of data goes hand in hand with serving scientific discovery, health, and many other ways to improve human lives. And finally, cost divided by quality. That's what drives our development. Efficiency is going to be, I think, a key part of getting us to personalization, AI on your device that's customizable to the specific needs of the user and runs at lower energy. I want to close by acknowledging the entire team that contributed here. Many students on that author list. Also partners that contributed various kinds of compute resources, Microsoft Azure, the NAIR in the United States, and Oak Ridge, which give us an allocation on the fantastic Frontier supercomputer. And I'll close by calling out that Wei Jiaxi, the chief author on FlexOlmo, is on the faculty job market. And some of our key young researchers, Somya Malik, David Heinemann, and Hao Shu, are applying to PhD programs. So if you're looking to take students, reach out to them and encourage them to apply. With the last 5 minutes, I'm happy to take questions. And in case the questions are not in English, I think I can listen.
We have a few minutes for question and answering. Do you have any questions? Please raise your hand. And please state your name and affiliation before you make questions. Anybody?
It's very dark in this room, so I can't tell if you're asleep.
Oh, yeah, second sensei, please.
Yeah, thank you very much for the great talk and into very detail. And you mentioned that the data flow, the circle of three components like data, model, evaluation. Yeah, it's clear that from data to evaluation, but could you give us some example from evaluation to data? Except you mentioned a little bit about this in the OCR, but
yeah, so remember that what we have to do for every phase of learning is decide, for example, we've decided on several sources and we need to mix them, right? 40% of this, 60% of that, or 50-50. Okay? In order to make that decision, you need to run an experiment and have an evaluation that you could reproduce. So the evaluations are going to influence the data sets that you choose.
I see. So in order to do so, evaluation is the key. So but how to evaluate? What's the purpose of this model to be?
You have to know that in advance, right? You have to decide, these are our goals with building this model. There's a lot of talk about generalist models, but ultimately, you know, I think you can't do everything, right? We made a big sacrifice on multilinguality so we could do all the other things that we do.
So you mentioned that AI for science, that is one of the purposes, right?
Yeah, and there are you'll see evaluations in our suite that are motivated by what we think AI for science will look like. But I'd love to see more in that space.
Thank you.
I'd love to have more scientists from across disciplines helping us figure out how do you evaluate.
Great. Thank you.
Yes, please.
So first of all, thank you for the very interesting talk. So my question might be a little bit broad, but do you have any plan at your institute to do anything related to like tools or agents?
Yes, absolutely. And the Instruct model, that's the one thing I didn't leave time for. Okay. But yeah, the Instruct model was developed with tool use in mind. Yes. And there's more work coming out about agents that I didn't prepare to talk about, but absolutely, we think this is essential. I think you know, there's a lot of things it doesn't make sense for models to do, right? Yes. And a lot of things that we all know we're AI researchers. We know the literature is coming out really fast.
Yes.
And building tools that can interact with a growing corpus of scientific literature is at the top of my mind. Yeah.
So what are some like unique challenges to like building a tool chain or a model that can use these tools?
Well, I mean, there's a lot of engineering challenges, right? So if you want your model to be able to learn new tools, you've got to be able to train in a way where it can actually run them, and that is an engineering challenge that I'm certainly not up to, but hopefully my team is. To give one example, yeah.
Okay, thank you very much.
Okay, thank you. I'm afraid it's about time to finish the first keynote. Professor Smith, thank you again for a very wonderful talk,
Thanks so much.
keynote.